Okay, in this video I'm going to describe how the 3 degree of freedom 6 unknown parameter identification is working by presenting a really good case, a marginal case, and a case where I was unable to identify coefficients. I'm going to start with my 20 bar 10k RPM data point because that is my best one. You'll see there are some sliders here that I use to set the frequency range of interest and do some filtering. And by filtering, I just mean exclude certain spectral lines that I know I don't want to include in the parameter identification. So right now I'm including all the data between 0 and 250 Hertz. And the first thing I'm going to do is eliminate spectral lines where the FRFs had a low coherence. And from experience, I know that a coherence of about 0.9 will include a sufficient number of points to curve fit, but deliver a sufficiently small standard deviation. The other thing I'm going to do is limit my bandwidth to about 160 Hertz. So on these plots you see two curves. The black curve is the thrust collar oil film dynamic stiffness that I solved for using a purely axial vibration model. And the blue curve is recreating those measurements but using a 3 degree of freedom model and these parameters that I can adjust with the sliders. From left to right, the parameters are a cross-coupled stiffness, a KXZ cross-coupled stiffness, that's what K0 is. K5 and C5 are the direct stiffness and damping coefficients of the drive-end hydrostatic bearing, and I need to include those as unknowns because that bearing was crushed during installation and its clearance is an odd shape, and the XL hydrojet code does not accurately predict these stiffness and damping coefficients because of the odd clearance. And then the last three are the axial stiffness, damping, and inertia terms of the thrust collar oil film. So I have these set to kind of an odd value right now, and the model is not matching the data. So I'm going to use these sliders to bring the black line and blue line into agreement. I've given myself the opportunity to change the sign on the cross-coupled stiffness term because I'm not exactly sure where it's coming from. So to give myself the best chance of matching data to model, I'm letting myself change the sign on that kind of arbitrarily. So these are okay. You'll notice there's this small aberration here. This is attributed to a rigid body mode where both the low-speed shaft and the high-speed shaft bounce on the angular contact ball bearings. And I don't want to include that in the curve fit, so when I click this checkbox, it exposes another slider that lets me remove frequency points between this low frequency and this high frequency. So right now, we're fitting data between 0 and 158 Hertz with a coherence of 0.9 or better, and we're purposely eliminating data between basically 70 and 80 Hertz. Let's see, let's do a little more fine-tuning on this. Okay, that's all right. Yeah. Okay. And then I'll adjust the inertia term to bring the model and the data into better agreement. So now my 3 degree of freedom model and my data are matched pretty closely, and I'm going to use the Levenberg-Marquardt nonlinear least squares algorithm to solve for these 6 unknowns. So the algorithm converged in 208 iterations, and the red line is the same model as the blue, evaluating using the 6 coefficients that the algorithm identified. And qualitatively, it looks pretty good. Both the real and imaginary part capture the data behavior of the data across the entire frequency range. Comparing my first attempt at parameter identification with this attempt and the predictions, the 3 degree of freedom model with 6 unknowns has improved the agreement between identified parameter and prediction. So originally I used a 1 degree of freedom purely axial model and came up with coefficients that were basically twice the prediction. This time around I'm much closer. So the XL thrust collar code identified or predicts a stiffness of 47 meganewtons per meter, and the nonlinear least squares technique identified 35 meganewtons per meter. so much closer. And the same is true for the damping estimate. So I started with this case, the 20 bar specific load, 10k RPM spin speed case, because these are my best data. Now I'm going to use a case that I think is marginal, but still workable, and that's the 40 bar specific load 10k RPM case. So again, I'm going to start with all the data, not going to filter by coherence, not going to remove any rigid body modes. And you can see that there are a lot more, the trend is not as obvious. So I have some dips here. I know these are associated with the low speed spin speed harmonics. This dip here and this dip here are that rigid body mode. 200 hertz, not sure what that is, but we're going to apply the same techniques we used before. So the first thing we're going to do is only retain data with a high coherence, and 0.91 is good. Okay, so these dips are still here, and I'm going to use this tool to remove those. These dips occur at pretty much the same frequency each time, each data point, that is, each point in the test matrix. Okay, so that's not terrible. I think we'll lower the bandwidth to maybe 200 hertz. We'll include the low frequency data. And again, I'm going to give myself the opportunity to change the sign on this cross-coupled stiffness term. This cross-coupled stiffness term, unsurprisingly, is what drives the low frequency behavior. So my approach has been to adjust this first to get the low frequency behavior to match. And then I adjust the thrust collar oil film stiffness to get this portion of the frequency response to match the model. So when I adjust KTC, you see that go up and down. And I can use MTC to adjust the curvature of the real part. CTC adjusts the higher frequency slope of the imaginary part. And K5 and C5 have some influence on both at lower frequencies. Okay, so that's good enough. Again, we're going to use the Levenberg-Marquardt algorithm. So for the best case, it took 208 iterations. For this case, it took 260. Qualitatively, it does a good job. It captures this low frequency dip in the imaginary part, the straight line slope through higher frequencies. It captures the similar behavior in the real part, and the identified coefficients are again in much closer agreement to predictions than they were with the 1 degree of freedom model. So I originally had 260 meganewtons when XL thrust collar predicted 122. And using this technique, I'm down to 171, and there's much improvement in the damping estimate. So that's also good news, but I expect when I propagate the uncertainty and calculate an R-squared value for this curve fit, it would be marginal at best. So the last case I want to illustrate is what I consider an untenable data point, and that's the 40 bar 20k RPM case. So again, I'll include all the data, won't filter by coherence, won't exclude any rigid body modes. Big swing in this data, so the y-axis goes from 1 E9 to negative 4.5 E9. The first thing we'll do is only retain data with good coherence. And by the time I get to 0.9, I've eliminated anything that exhibits a trend. I don't see a trend in these data. Dropping to 0.8 doesn't really help. Even 0.7. So for this one, we'll leave it at 0.8. I'll lower the frequency range of interest to maybe 200 hertz. 190 hertz. Let's do this. Okay. I don't see a rigid body mode here that I want to try to fit, or try to remove rather, so I'm not going to use this tool. And I'm just going to do my best to match the blue line to the black line. You know, adjusting the sign of K naught in this case doesn't make much difference. The trend is very hard to see if it's there at all. yeah, this is kind of a fool's errand. So just for the hell of it, we're going to try to fit it. 260 was our last number of iterations. We'll see. Okay, 767. And it looks like we've gotten worse. Again, if you calculated the R-squared value for this, very low. No agreement between the red line and the black line. The identified thrust collar oil film coefficient is worse than the 1 degree of freedom model. I guess damping's better, but does the red curve really look like the black data? I don't think so. So that's where I am using this 3 degree of freedom model with 6 unknowns and a nonlinear least squares algorithm. I would say that roughly half of the data points in my 9-point test matrix are fittable. 4 or 5, so maybe I can fit 4 or 5 okay. 4 or 5 are not workable, and at this point I don't have an uncertainty for any of these coefficients, which is frequently the showstopper for parameter identification.